So hi everybody, and thank you very much, Katja, for the invitation to give this talk. Can you hear me?
Yes.
Okay, good. Yes, so the title of my talk is the Linearized Calderón problem on cylindrical Riemann manifolds and exponentially accurate solutions. So my talk is based on a joint work with Katja Krupchuk and Mikko Salo. One of the reasons I'm going to talk about this specific paper or specific topic is that I have a feeling that our paper might not be so accessible for easy read. So I will try to help potential people who might be potentially interested in the paper. Okay, something wrong now. Okay, good. Okay, so outline of my talk. Just a short introduction to Calderón problem, and then I will go to the main topic. So I will discuss beams with exponentially small error to some detail, and then I will prove our main theorem, and lastly there will be a short summary. Introduction. So I'm going to talk about our work in the setting of anisotropic Calderón problem. In general, the anisotropic Calderón problem is the following. So if Mg is a Riemann manifold with boundary, the anisotropic Calderón problem is to determine the manifold from the knowledge of the DN map, and the best possible recovery is up to a diffeomorphism. So let us shortly define what is a DN map. I'm pretty sure all of you know it. But anyways, so let W be the solution to the Riemann Laplace equation. So here the Laplace G is the Laplace-Beltrami operator. And for this equation, we give the boundary value F. As usual, the DN map is then defined by the assignment that you give the boundary value F. Then you solve the Laplace equation, in this case, and then you compute the normal derivative of the solution on the boundary. Today, we are going to study a variant of this general anisotropic Calderón problem. This is a little bit easier, but still quite hard. The problem is to determine an unknown potential Q on a known Riemann manifold from the Dirichlet to Neumann map of the Schrödinger equation. So the Schrödinger equation is here on blue, and the DN map for this equation is defined by the same assignment as above. And we aim to recover the Q from the DN map. Right. So the determination of this potential function Q in general, or in general Riemann manifolds, is open. I would say quite wide open. But there has been some considerable progress in the setting of so-called transversally anisotropic manifolds. I will abbreviate these manifolds by TA. So what are transversally anisotropic manifolds? These are Riemann manifolds, which are subsets of a cylinder. They can be also the full cylinder. And here I have a picture of the situation. So here this axis going up, this is the Euclidean direction, R. And each of these slices of this cylinder here, these are this manifold M0 with the Riemann metric G0, and this M0 G0 is called the transversal manifold. So why these manifolds has come up in the research, or why they are nice? The reason is that these kind of manifolds have an analog of complex geometric optics solutions. And I will explain later what I mean by those. Okay, so let's look at the earlier results in this setting. So this business was started by David dos Santos Ferreira, Carlos Koenig, Mikko Salo, Gunther Ullmann in 2009. They initiated the study of the Calderón problem on transversally anisotropic manifolds. They were able to prove that if the transversal manifold, so recall that M0, G0 is the transversal manifold, they were able to prove that if the transversal manifold is simple, then they can recover the unknown potential Q from the DN map. So roughly speaking, a manifold is simple if all of its points are connected by unique geodesics. Then, some years later, again David dos Santos Ferreira, but now with Jaroslav Kurulev, Matti Lassas, and Mikko Salo, they were able to prove a similar result. In this case, they assumed that the geodesic rate transformation on the transversal manifold is invertible. However, it is not completely known when the geodesic rate transformation can be inverted. And also there are counterexamples which shows that always you cannot invert the geodesic rate transformation. Then again, a little bit later, David dos Santos Ferreira, Jaroslav Kurulev, also known as Slavo, Matti Lassas, and me, and Mikko Salo, we started to study this problem from a slightly different angle. So instead of trying to recover the Q fully, we started to study the singularities of Q. And our method uses different geometric conditions on the transversal manifold. In particular, we made no assumptions on the invertibility of the geodesic rate transformation or that the transversal manifold would be simple. The main technique in this paper was that we used solutions which corresponded to intersecting geodesics. And this is one of the topics of today, and I will explain what I mean by this intersecting geodesics and the solutions. Okay, so actually we are going to make things a little bit simpler even. So we are only going to study the linearized Calderón problem on cylindrical manifolds, so on these TA manifolds. The linearized Calderón problem of determining Q from the DN map of the Schrödinger equation, this amounts to showing that if the integral identity which integrates f against the product of two harmonic functions u1 and u2 is 0, that should imply that f is 0. So this is the standard linearized integral identity of the linearized Calderón problem. So this, for example, holds also on domains of Rn. Next, I'm going to explain what is our main result, which we did with Katja and Mikko. But before that, I need one definition, which is the geometric condition we use in the theorem. It goes as follows. So let gamma 1 and gamma 2 be two geodesics that intersect the boundary transversally. Another word for this is that gamma 1 and gamma 2 are non-tangential. Now the vector z0 psi 0 in the tangent space of the transversal manifold, so M0 was the transversal manifold, it is said to be generated by a pair of geodesics gamma 1 and gamma 2 if gamma 1 and gamma 2 intersect at this point z0 and the velocity vectors of these geodesics at that intersection points sums up to this vector psi 0. Moreover, this pair of geodesics gamma 1 and gamma 2 is said to be admissible if they generate this z0 psi 0 and they only intersect once, which means that they only intersect at this point z0. Okay. So next is the main theorem. Okay, so this is our result, which we proved last year. Before that, I need a small explanation here. So in this cylindrical setting, it is natural to split the variables into two parts. So a function will have its variables x1 and x prime. So x1 will be the variable in the Euclidean direction, this real line r, which went up in the cylinder, and x prime is the variable or coordinates on the transversal manifold. So these are the slices of the cylinder. And I also need to have this kind of definition here that f hat lambda, where this dot is a free variable on the transversal manifold. This denotes the partial Fourier transformation of f in the direction in the x1 variable at the frequency lambda. Okay, so given this is our theorem from last year, Katja, Minä, me, and Mikko. So let MG be a transversally anisotropic manifold. And now we make this assumption that this transversal manifold is analytic. So note that our manifold is known, and in this case we assume that the transversal manifold is analytic. However, we only assume that our unknown is in L infinity, so the unknown can be basically anything. And we assume that it satisfies the condition of the linearized Calderón problem, which is this equation 1 here. So U1 and U2 were harmonic functions. Now, if we take a vector from the tangent space of the transversal manifold, Z0, Xi0, and we assume that it's generated by an admissible pair of geodesics, so this gamma 1 and gamma 2s in the previous slide, then for any lambda, we have that this vector Z0, Xi0 is not in the analytic wavefront set of this f hat lambda. So WF is of course the wavefront, and A refers to the analytic wavefront set. I will discuss this analytic wavefront set a little bit later on as well. A corollary of this theorem is the following. So if each tangent vector on this transversal manifold Z0, Xi0 is generated by an admissible pair of geodesics, then the linearized problem is solvable, meaning that f is identically 0. I will explain this, why it is so. Okay, so now we are going to discuss Gaussian beams with exponential small error.
May I ask a question before you go any further?
Okay.
You say M is contained in R cross M0, but it doesn't have to be all of it.
It doesn't need to be all of it.
Thank you.
Yes. So it was the picture with the pink area inside the cylinder. Thank you very much. Okay, so before I go to Gaussian beams, I will try to motivate why we are going to discuss those. And for that, I will sketch the proof of the main theorem, the theorem on the last slide, and also its corollary. So the proof consists of two major observations. And again, we denote the points on the subset of the cylinder, as James asked, by x prime, x1 and x prime. And now the point 1 is that because we have this cylindrical geometry, so that it's topologically it's R times M0 or subset of that, we are able to construct an analog of complex geometric optics solutions, CGOs, and we actually can do them so that the correction term is exponentially small in a precise sense, which I will explain. So what are CGOs? CGOs on a cylindrical manifold. So cylindrical manifolds is the same as transversally anisotropic manifold. They solve the Laplace equation now. And they are of the form U is e to power s x1 times, in brackets, vs, and now the function which depends only on the transversal variable is x prime, and then there is r. So r is a correction term as usual, and s will be a parameter which is large. So now, since this transversal manifold is analytic, we are actually able to show that r, the correction term, can be taken to be exponentially small in this large parameter s. The second point is this. So in our earlier work with David and Matti and Slava and Mikko, I think that was all of us, we observed that the integral identity of the linearized Calderón problem for certain CGOs on cylindrical manifolds leads to an integral transformation called FBI transformation of this unknown f. Now, since the error term, we were able to solve that it's exponentially small. Then a feature of this FBI transformation, which I will explain later, allows us to study the analytic waveform set of F. Then, under the assumptions that all the vectors on the transversal manifolds were generated by admissible geodesics, it follows that this F hat lambda, which was the Fourier transformation of the unknown F in the x1 direction, is actually analytic. That means that we can make boundary determination on the M0 on this transversal manifold to recover the F hat lambda for any lambda. Then finally making a Fourier transformation in the x1 direction, in this lambda direction, we can actually recover F. I will explain this again later. So, but this is the sketch of the proof. And let's go to the Gaussian beams next, or CGOs. So the proof of our new results, they depend heavily on the properties of Gaussian beams. As I already said, a CGO on a transversally anisotropic manifold has the following form. So U solves Laplace U is 0, and it has the form e to the power minus sx1 times in brackets v x prime and then r. And now we take this v. I didn't specify what this v was earlier, but I will explain what it is. So we take this v, it will depend on this parameter s, large parameter s. This v will be a so-called Gaussian beam. The Gaussian beam is an approximate eigenfunction on the transversal manifold, and now it has energy s squared. In fact, our large parameter s is complex. We also call it complex frequency, and it is of the form tau, which is large, and then we have I times lambda, and lambda will be the Fourier variable in the x1 direction. But lambda in a sense is fixed, and r is the correction term, as I said earlier. Okay, so why do I call this CGOs? So let's compare the situation to the Rn. So in Rn, the CGOs have the following form. They are e to the power minus tau eta dot x times, in brackets, e to the power I tau xi dot x plus the correction term, where now eta and xi are orthogonal. So note now that if you consider that eta is the x1 direction, so then this term here, by the way, can you see my pointer? I hope you do. So this e to the power minus tau eta dot x corresponds to e to the power minus s x1. And now this e to the power I tau xi dot x, that is actually an eigenfunction of the Laplace equation on the hyperplane, which is now orthogonal to this vector eta. So now you see the correspondence. So we have sort of like a exponentially large factor, which is actually an eigenfunction of negative energy in front. Then in the brackets, we have an eigenfunction on a set which is orthogonal to this x1 direction or similar to the eta direction. And this v is an eigenfunction or approximate eigenfunction on this orthogonal space. So this is the reason why I call this CGOs. Okay. Moreover, the Gaussian beam is actually a special eigenfunction on the transversal manifold, and it has the property that if it's constructed with respect to a given geodesic, gamma t here. Now, if t and y are coordinates near this geodesic gamma, where t corresponds to the geodesic parameter, and y are coordinates which are transversal to the geodesic gamma, then a Gaussian beam has the form that it's e to the power s times a phase function phi, times in the brackets we have the amplitude. This kind of decrease in power series in tau is called an amplitude, which starts with a0, which is a function on m0. Then we have a minus 1, which is a function on m0 divided by tau, and then we would have a minus 2 divided by tau squared, and so on. And, well, S is the complex frequency now here. So what is the qualitative behavior of these Gaussian beams, it's the following. So this phase function has the leading order coefficients are I times t minus positive constant times y squared. So what it means that, think about this s now just as this tau here. So with this phi here, the phase function, or what you have in the exponent of this e, is I times tau t. So it means that when you travel to the direction of the geodesic, the solution will oscillate. And when tau is large, it will oscillate very fast. Also, when you go away from the geodesic, then you will have a Gaussian decay to that direction due to this factor here. So the construction of Gaussian beams, it's very well known. But typically, in the literature, it is satisfied to have only a polynomial decay in tau, and we will have an exponential decay in tau. We actually expect this theorem, which we proved in our paper. It might be known to some expert, maybe in some related fields in mathematics, but we could not find a proof, so we proved it in our paper. So let's see that. So let the transversal manifold be analytic now, compact with boundary. Let gamma be a non-tangential geodesic, and lambda be fixed, and S the complex frequency tau plus I lambda. In this case, there is a family of functions V, which are now parameterized by this complex frequency S on the transversal manifold, and a positive constant C, so that these functions V's are supported near the geodesic gamma, and they satisfy this condition here. So the L2 norm on this transversal manifold of minus Laplacian minus S squared, it's not completely zero, but it's exponentially small. Of course, note that if this would be a zero, then V would be an exact eigenfunction. Since it's only small, we call it approximate eigenfunction. Right. So let's also record some features of these Gaussian beams. So in our setting, we actually allow the geodesic to have self-intersections. So if a P is a point on the graph of geodesic gamma, it might be that the geodesic have NP self-intersections at this point P. So let T1 to TNP be those intersection times. In this case, on the neighborhood of this point P, we have that V is the sum of NP functions, where each of these functions VL has the form e to power I s phase function times an amplitude function. An amplitude function means that it's like a decreasing series in the negative powers of tau. And then it has this phase function has some characteristic properties. The first one here, that the phi, when we restrict that to the geodesic, it is t. So this is the feature which gave the Gaussian beams the oscillation along the geodesic. And then the last condition here, which says that the imaginary part of the Hessian of this phase function phi to directions which are orthogonal to the geodesic is positive. So this is the feature which gives the Gaussian decay away from the geodesic. Moreover, in this theorem, we proved that this phase function phi is actually analytic, and AL is something called elliptic classical analytic symbol. And I will explain later what that means. Okay. So as I said, the theorem might be well known to some, but its proof, how we prove it, it contains some nice features. And I have a feeling that it might not be well known to many. So for that reason, I decided to discuss how these Gaussian beams are actually constructed. And in my opinion, there is some nice techniques. Okay, so let's construct the Gaussian beams. So Gaussian beams, they were local sums of the functions of this form e to the power I s phi times the amplitude A. And as usual, they are constructed in 2 steps. And here what follows, I will just put S to be this real parameter tau, to make the formulas shorter. If S would be tau plus I lambda, the principles would be the same, but the formulas would be longer. Now, if you have this kind of ansatz for V, so I call this ansatz, I call this ansatz. And if you apply minus Laplace and minus tau squared to this ansatz here, and then you multiply by the negative of the e to the power minus I tau phi, you will get this kind of equation. So now we see two types of things here. So there is like the leading order thing is tau squared, and it is multiplied by this kind of object. And then we have lower order terms. Here we have tau in front, and here we don't have anything in front. So the construction goes as usual. So we first find a phase function phi. In our case, it will be an analytic function, which solves the so-called diagonal equation here. So you see that in this case, this term will be equated exactly to 0. Then when we have solved the phase function phi, we insert that phi to the remaining part of here. So we equate this, which are now painted to blue, to 0. And this gives the so-called transport equation. And now for a reason which I will explain, it is convenient to write this part here as a vector field capital L. And we also assume that A is an amplitude, which means that it has a decreasing power series. Okay, so let's solve the diagonal equation. So I would say often, at least what I've seen in the literature, the diagonal equation is solved only approximatively by a certain Taylor expansion argument. So if you're familiar with this argument, this is the argument which, for example, leads to solving the so-called Riccati equation. We instead use a different method. We use the machinery of Lagrangian manifolds, which I now explain. We view the diagonal equation, this d phi inner product d phi equals 1, or d phi squared is 1, as the Hamilton-Jacobi equation for the function p, which now is a function on the tangent space or cotangent space, if you will. And it's defined by psi squared with respect to this metric g minus 1. So this is in local coordinates, you have the Riemann metric matrix here, and you multiply the vector psi, and then you take the Euclidean inner product against psi in coordinates. So the Hamilton-Jacobi equation is the equation of this form here. So here the first one. So now if you plug in place of psi d phi, you will actually see that this first equation here, that is equivalent to the diagonal equation, which was this one here. So this Hamilton-Jacobi equation is a nonlinear PDE. That's because the diagonal equation is a nonlinear PDE. And now we use coordinates, this ty. So remember that these coordinates were so that t is correspondent to the direction of the geodesic, and y were coordinates which are transversal to the geodesic. And this is an initial value problem in the sense that we consider this set 0, y, as the initial data surface. Well, it has the dimension of the manifold minus 1. And we specify the initial conditions, which are these two guys here. So we specify that the gradient of phi at the origin is a vector psi 0. And also we specify that the phi on the initial surface is a given function psi. And a solution for this Hamilton-Jacobi equation can be found by constructing a Lagrangian submanifold of the cotangent space of the transversal manifold as follows. Okay, so there will be 3 slides about solving the Hamilton-Jacobi equation. Let's start. So again, t and y are coordinates on the neighborhood of the geodesic. T was the geodesic direction and y was the orthogonal directions or transversal directions. In this case, the tangent bundle, which in local coordinates is now a subset of Rn times Rn. It is parameterized by t, y, and then the conjugate variables tau and et. And let's now look at the picture. on this slide, we are going to define what are these black arrows in this picture. So let's see what we have here. So, sorry. Yes, so here on the, I hope you see this, on this blue line here, this is the initial data surface. So we start the definition of this, or how we define these black arrows, by setting psi 0, which was one of the initial conditions, to be the velocity vector of the given geodesic gamma at time t0. Since our geodesic is unit speed, it solves the peak psi, the equation peak psi 0 is 0. So gamma 1 squared is 1. It means this peak psi 0 is 0. And then there's a technical part. By the implicit function theorem, we can actually parameterize this variable tau in y and eta, so that the equation p is 0 is solved by these kind of variables. So we set t to 0, y is free. Then by the implicit function theorem, there's a function lambda which parameterizes the tau variable here, and then we have eta free. Moreover, we want to implement the initial condition of the Hamilton-Jacobi equation, and for that, we need to choose eta to be the y gradient of psi. So with this, we have defined these black arrows. This one here. I will go to the next slide, and there will be the same picture. Okay. So as said, the black arrows were given by these conditions. So t was 0, y is free, tau is given by this lambda function, the implicit function, and eta was given so that the initial condition is satisfied. And actually I have written here that y belongs to Cn-1. So this is just, I wanted to highlight this, that since we are going to find an analytic function or analytic solution for the phase function, it's actually natural to work in the complex domain. Okay, so we have a set lambda prime, the black arrows. So now let H be the Hamiltonian vector field, which is a vector field on the tangent bundle of the manifold X. So X will be is the transversal manifold M0 also. So it's a vector field, so it means that it's a mapping from dx to ttx. I have written here the P again. So now, since this is basically the psi squared, the integral curves of the flow of this Hamiltonian vector field HB are actually geodesics. This means that the velocity vectors of the geodesics are curves in the tangent space of the transversal manifold, which is here X, capital X. So now comes a point, a punchline. So now we have set these black arrows to solve the P is 0 equation. And now the Hamiltonian flow preserves actually P. That means that if we set lambda to be the set, which is achieved by flowing out lambda prime, flowing out the black arrows, this set actually satisfies that it's P of that is 0. So P lambda is 0. And these curves which are gained by flowing out by the Hamiltonian flow are these red curves here. Right. The fact is that now by construction, this lambda, the red curves, it's actually a Lagrangian submanifold of the cotangent bundle. And now here C is that because we look for complex solutions. So we have this kind of notation. The fact also is that since lambda is a Lagrangian submanifold, we can actually parameterize that by a function phi locally. So U is now an open set on X on the base manifold, which is M0. So that lambda locally, I use this notation, it is of the forms of points X and D phi of X, gradient phi X, and X belongs to U. So now the red curves solve the equation P is 0. And now we see that actually because lambda was given by this kind of points, so if we substitute that to P, we have that d phi g at point x minus 1 is 0. So we actually see that this parameterizing function of this Lagrangian submanifold solves the diagonal equation. This is pretty cool in my opinion. So we have found a local solution to the diagonal equation by this method. Okay, so this is a local construction, and we actually must patch up the construction to have a global solution on the neighborhood of the original theoretic gamma. For that, we need to be a little bit careful, and to have a global solution, we choose an initial data psi, which was now a function on the initial data surface, so it depends only on y, so that the imaginary part of the Hessian of psi is positive. With this choice, we may use the theory of positive Lagrangians. I don't go there what those are, but by using the theory of positive Lagrangians, we can have a global solution to the diagonal equation. And I remind here people who are familiar with the construction of the solution to the diagonal equation by using the Taylor series argument, that this is a part which is analogous to choosing initial data with positive imaginary part for the Riccati equation, and showing that this condition is preserved by the solution to the Riccati equation. So choosing this kind of initial condition guarantees that the solution doesn't somehow collapse before its time. Yes, so now we have solved the diagonal equation. Let's go to the amplitude. We have found the phase function phi for this Gaussian beam ansatz, which was discussed.
Sorry, Tony, can I ask you a question?
Yes.
The first part of the construction, I mean, could you do it, I mean, in a sort of the pedestrian way by solving it by, I don't know, making a Taylor series or whatever, like, and then can you somehow solve the icon version in that way instead of using this nice way that you presented?
Yes, so that is, I would say that is the typical way to using the Taylor expansion argument. However, in our case, if we try to use that, the problem is that we want to have some kind of analytic solution. We want the phase function to be analytic, and we were not able to construct an analytic solution by using the Taylor series method. Does that answer your question?
Yeah,
no?
Okay. I didn't catch all of that, but yeah, I think.
Okay, so maybe we discuss this log more. Okay. Yes, right. Okay, let me continue. So we have found the phase function, and then the second step of the construction of Gaussian beams was to insert the phase function to the so-called transport equation. And the transport equation was this equation here. And again, I remind you that L was given by, it is a vector field, so it's a differential operator of order 1, and it operates on functions here in A by this formula. Okay, so we look for, as an amplitude function, we look something which is classical analytic symbol. And what is a classical analytic symbol? A classical analytic symbol is a symbol, which means that it's of this form, this kind of negative series in taus, and it satisfies two conditions. First, it has some kind of growth condition in the index k. So ak is bounded by some fixed constant to power k plus 1 times k to power k. And the other condition is that ak needs to be an analytic function in the variable x. So now this L is a vector field. So that's sort of like a beneficial thing. So if you go to a flow out coordinates of this vector field L, it means that in these coordinates, the integral curves of the vector field L, they just look like straight lines. So L corresponds in these new coordinates just to a coordinate vector field dou r here, which means that if we just integrate in R, we can solve the transport equation. So it's pretty easy in that sense.
Can I have a question?
Sorry?
Yes, can I have a question? Here,
Yes,
you see your transport equation have been obtained in terms of order of tau, but now that equation you have the first order term in terms of tau and the zero order term with the active to the Laplacian or A. So how you call how can you make them coexistent?
Yeah. So in this setting, I understand your question. In this setting, this solving the transport equation goes a little bit like slightly differently. So I would say that your question is related to the usual construction where you actually solve by equating the powers of tau, and you solve this A case individually. So you will have like capital N equations. However, in our setting, actually it's more beneficial to sort of solve all of these coefficients A, K simultaneously. So it's just a fact of this method. And yeah, I understand your question. Maybe we discussed a little bit later.
Okay, yeah.
Yeah, because I'm running out of time. Okay, right. So now to show that this integration produces a classical analytic symbol so that it satisfies these two conditions near the geodesic gamma, we actually need to use this kind of method called nested neighborhoods. And this is a method which goes back to a paper by Sjöstrand, and in my opinion, it's a non-trivial step. And it's also to relate to this Chia-Ling's question. I will give you a reference to this Sjöstrand's paper in the end. Okay, so let's complete the Gaussian beam construction. So we have now found the phase and amplitude functions, and we may study how large is the error for this ansatz e to the power is phi times a to be a true eigenfunction of the Laplacian of energy s squared. And again, here I will just denote s by tau to make things simpler. So now comes a small punchline. So we actually let this capital N, which was the length of the amplitude expansion, this guy here, we let that to depend on tau. In particular, it means that when we are going to take tau to infinity or consider large taus, it means that n tau will actually go to infinity. And now since phi solves the eigenvalue equation and a was the solution to the transport equation, then actually a small calculation shows that when we apply minus Laplacian minus tau squared to the ansatz, so this guy is this guy here, what is only left is tau to the power minus n, and then you have Laplacian of the last amplitude expansion term an. Now, since this a was a classical analytic symbol, we have that its second derivatives, and especially its Laplacian, the Laplacian of an will be bounded by the values of an itself. So this is by the standard Cauchy estimates. And also we have the second condition for the classical analytic symbol, which means that these components ak have the growth condition, which for an mean that it's bounded by some constant to the power n plus 1 times n to the power n. So if you plug in these two conditions here, you will see that this right-hand side is bounded by tau to the power minus n, c to the power n plus 1, n to the power n. Now if you make n to depend on tau, so that n tau is tau divided by e, so this is the Neper constant, and then c, which you see here, you actually see very easily that this right-hand side is bounded by a constant c times e to the power minus tau divided by e times c. So this is a positive constant here. So this gives the exponential decay of the Gaussian beams. Okay, then we go to the proof of the main theorem. So we have now discussed how to construct the Gaussian beams, and let's now discuss how we choose them in the linearized Calderón problem. So recall that S was tau plus I lambda, tau was large, lambda was fixed, and recall that the Gaussian beam looked like e to the power I tau t, so oscillation in the direction of the geodesic, and an exponential decay away from the geodesic. So now some observations. So in inverse properties, concentration is typically good, but oscillation is bad in the sense that when you integrate against an oscillating function, the non-stationary phase can kill information of the f of the function which you integrate against, in our case the unknown f. Okay, so however, if we plug in the CGO solutions, which were of this form, so this exponential large factor e to the power sx1, then the Gaussian beam, and then the correction term, we get the following identity. So this is the identity which follows from the integral identity of the linearized Calderón problem, which was that f integrated against a pair of harmonic functions is 0. And now this right-hand side is exponentially small. Why is that? Well, it's due to the fact that this B was a Gaussian beam with exponentially small error. And also to get this one here, we use the standard Calderón estimates in this business. Now we are free to choose the geodesic gamma and eta, which corresponds to the Gaussian beams V1 and V2 in this identity here. And I will make this small remark here. So now we are free to choose this gamma and eta. If you would choose eta, the other geodesic eta, to be the geodesic gamma, just travel to the opposite direction, the oscillation would actually cancel. So why is that? So you see here that the Gaussian beams look, so this is like V1 here. And then if you multiply that by a similar function with the t opposite sign, the oscillating factor here, they will exactly cancel. In that case, if we take tau to infinity, so the large parameter to infinity, we would get the integral identity you see here. So in that case, the f hat, the Fourier transformation in the x1 variable, integrate against the geodesic gamma, and then there's some attenuation factor, is 0. And it was observed in a paper by David dos Santos Ferreira, Jaroslav Kurulev, Matti Lassas, and Mikko Salo. And this identity actually reduces to inverting the geodesic ray transformation on the transversal manifold. We are not going to do that. We instead choose Gaussian beams, which correspond to intersecting geodesics gamma and eta. So in that case, the product of the two Gaussian beams, V1 and V2, to the leading order, they look like e to power I s sub vector psi naught dot x minus a, where a is positive, s psi squared. I'm sorry, here should be x prime and x prime also here. So why is this? So let's look at the picture. So we have the geodesics gamma and eta, and the Gaussian beam corresponding to this gamma, it oscillates when you travel along the geodesic, and it has exponential concentration to the geodesic. Similarly, the eta oscillates and has Gaussian concentration. So when you multiply these guys, they concentrate exponentially near their intersection point. It's this pink area here. But you are still left with oscillation to a direction, which is what? The direction is the sum of the velocity vectors of the geodesics. So psi 0 is the sum of velocity vector of the geodesic gamma plus the velocity vector of eta at this intersection point. So now what we have gained is that we have an excellent concentration to the intersection point. So it's very good. So it sort of looks like an approximate delta function on this pink area. But there's still this oscillation, which kills information by the non-stationary phase. So in particular, we cannot take tau to infinity. If we would take tau to infinity, we would actually lose all the information of the unknown f in our case. Right. So what we are going to do, so we cannot take tau to infinity, but we do the following. So what is an FBI transformation? I need to discuss that now. The FBI transformation of a function now on Rn is a transformation which takes f inside, and you evaluated that to direction psi. It's given by this formula that it's integral of f against e to power I psi dot x minus beta x squared. So this the I psi dot x is sort of like, it's a Fourier coefficient, and then you have a Gaussian concentration to a point. This FBI transformation, it was originally used by Bruce and Eigelnitzer to actually study exactly the real analytic wavefront set of functions. So the f in this transformation is Fourier. So note now that the kernel of the FBI transformation, it almost looks the same as the product of two Gaussian beams, V1, V2. And as we discussed in the previous slide, it roughly looks like e to power s psi dot x minus as psi squared. So if we choose, in particular, if we choose s psi naught to be psi and as to be b, we see that this guy here looks exactly like this guy here. Okay. And now we need one fact. This is now in Rn. So let psi not be a vector in Rn, and assume that this psi naught has a neighborhood. So now we vary both the base point of the vector and also the direction. So this neighborhood is in Rn times Rn. Use a neighborhood of psi 0. And we assume that for all psi's in this neighborhood U, the FBI transformation of function satisfies this exponential decay condition. If this is true, then by some theorem, psi naught is not in the analytic wavefront set of f. So this is not in Rn, but this is, I guess, quite well known.
Just a question here. Psi
Yes,
naught
please.
is only in Rn, so how can there be a neighborhood of it in Rn cross Rn?
So in this business, it's yeah, I tried to explain this. So so psi naught is how do I explain? So psi naught is one vector, and then you define its neighborhood in the tangent space of Rn. The tangent space of Rn is topologically Rn times Rn.
Oh, it's
So that's sort of the point, and
Yeah.
this is quite typical in this this kind of is this now some kind of micro-local setting? I'm not sure, but yeah, that is what it means. Thanks very much.
okay.
Yes, but the FBI transform should be in the phase space. Then you have a certain center in the x space, right? So here you by default you assume that the x center is at the
I cheated a little bit.
yeah.
So yeah, you're absolutely correct. So I cheated in this formula a little bit. So in more generality, you should have like x minus, let's say, y in place of here.
Yeah.
So yeah, I cheated a little bit. Yeah. Okay, but let's go on. Okay, we are almost done. So let's just, this is the end of the proof of our main theorem. So let's combine everything we've got. So we have the equation 3. So let's start from the right. So this equation here, that was the result of the integral identity of the linearized Calderón problem applied to CGOs with exponentially small error in the corresponding Gaussian beams V1 and V2. And then what we discussed a little bit earlier is that V1 and V2 in the highest order, it looks roughly like this function here. So that gives this identity here. And I have a little bit also maybe cheated here. I put A to contain all the amplitude functions and also the higher order components of the phase function. It's not very important what this capital A is. It just needs to be positive. So now, so recall that V1 and V2, they corresponded to intersecting geodesics gamma and eta. So now if we vary the geodesics a little bit so that they intersect not at the point it was Z0, but a little bit away from Z0, and also if we perturb the direction of the geodesics a little bit, we can make the sum of the velocity vectors, which was this psi0 here. We can also make the psi0 vary a little bit when we change the geodesics. So actually we can make this tree to hold in a neighborhood U of psi0, which is now a set of the tangent bundle of M. And as I guess James asked, this is locally now a subset of Rn times Rn. Okay. Yes. Okay. We have the similar theorem for the wavefront set in this setting. And from this condition 3 for this neighborhood U, it follows that psi0 is not in the analytic wavefront set of f hat at the Fourier variable 2 lambda. So I will remind you that this dot variable here is the variable on the transversal manifold. Okay, this sort of gives our main theorem, which was this condition actually. Right. Now, if all of these vectors psi0 on the tangent bundle of the transversal manifold are generated by admissible pair of geodesics, then actually it follows that there is analytic wavefront set of f is actually empty. Okay, so that is equivalent to saying that f hat 2 lambda is analytic, where so this dot now belong to the transversal manifold, which was M0. Okay. Right. So now recall that in the uniqueness proof of the linearized Calderón problem, this unknown f is actually the difference of the potentials Q1 and Q2. We wanted to show that Q1 is Q2. Then by boundary determination on the transversal manifold M0, boundary determination means that we can determine the Taylor series of Q1. We can show that the Taylor series of Q1 is the Taylor series of Q2, which means that the Taylor series of f vanishes. And since f is analytic on the transversal manifold, it means that f hat 2 lambda dot is identically 0 on the transversal manifold. And this can be, we can make this happen for all lambda in R. And then the final step. So now we make the Fourier transformation in this first variable, which was the Euclidean direction. So we make the inverse Fourier transformation in x1 direction. And this shows that f is identically 0, which is equivalent to that Q1 is Q2. So this solves the linearized Calderón problem under the assumptions we had. I think I'm almost done. One slide more. Right, so let us recall what we had. We had a new result on the linearized Calderón problem on this transversal anisotropy setting. So the manifolds which looked like subsets of cylinders. The main assumption was that the known geometry is assumed to be analytic, but the unknown potential Q can be basically anything in L infinity. The proof was based on a new method which used two things. First, we constructed exponentially accurate quasimodes, which corresponded to intersecting geodesics. And in the recovery of the unknown, we used the FBI transformation. Some points. This method, it does not involve inverting any integral transformation. So I guess that's in a sense good. And then I remind you that we had this construction of the phase function of the Gaussian beam. So sorry, this quasimode should be Gaussian beam. The phase function of the Gaussian beam was constructed by a Lagrangian submanifold argument. So I like that argument, and maybe you haven't seen that before. And then there was this geometric assumption to solve the linearized Calderón problem, and this was that all the vectors on the tangent space of the transversal manifold needed to be generated by admissible pair of geodesics. So I didn't discuss this condition much. Here I make one comment. So since in this Urban series of talks, there has been, I guess, some talks about inverse problems for nonlinear equations. So I mentioned here that in the corresponding problem for nonlinear Schrödinger equation, this admissibility condition can be removed. So if people are interested in the nonlinear settings. Right. And final remark, our proof, in my opinion, it's not completely satisfactory. So our unknown could be in L infinity, but in the end, the reconstruction of the unknown potential Q was by analytic continuation from the boundary. So what this means is that, for example, if you try to do a stability result by this method, I would expect that you don't get very good. And this also begs a question that can you use this exponentially accurate solutions by some different means? And maybe I can say that we are working on this question currently. So this ends my talk. Here is the references which I used. And I would like to thank you at this point. Thank you very much.
Thank you very much, Tony, for the very nice talk. Are there any questions or comments, please?
You had many questions during the talk, so please ask.
Okay, I have a question.
I missed the first minute. So you proved linearization is injective, like at the potential equals 0. Is that correct?
Yes, it's correct.
Okay.
Yeah.
So yeah, and in general, this is of course not available. Although the injectivity for the analytic metrics is known, like the uniqueness part of the Calderón problem, right?
Was that a question?
Say again?
Could you please repeat?
Yeah, so I'm just making a remark. The injectivity, the uniqueness part of the Calderón problem for analytic metrics is known by a paper
Yes.
by Lasas and Ullman, I think, or something like that.
Yeah. Thanks very much for the question. Yeah, that's very nice. So I tried to highlight the point that the known geometry, I will maybe go a little bit back here. So the known geometry which you do not recover, you just assume that you know it. That is assumed to be analytic. But the unknown, it's not. It's just in L infinity. So in particular, this by no means follows from the paper by Gunther and Matti.
Mm-hmm.
So the known geometry is analytic, well, yes, but the unknown is basically anything.
Okay, and just a secondary question, this geometric condition, I mean, is it, what kind of geometries satisfy this condition?
Yeah, that's a good question. Actually go there. Right. So we actually used this condition in our earlier paper as well. And in that paper, so this earlier paper was with David dos Santos Ferrer, Jaroslav Kurlev, Matti Lassas, Mikko Salo.
Right. It's where you recover the wavefront set of the potential or something like this.
Yes, exactly. Yeah. And so in that paper, we actually characterized this geometric condition in the sense that it is satisfied if the transversal manifold satisfies a certain condition, which we called, I think, Stefanov-Ullman regularity condition or something like that. What is it's a little bit hard to explain in a couple of words, but in the earlier paper we characterized this condition by using the Stefanov-Ullman regularity condition, which has been studied earlier in inverse problems. So
and I guess you get some examples also there. Okay.
Yes. Okay. Thanks very much.
Thank you.
Thank you. Are there any other questions or comments, please?
Yes, I do. So when you construct a solution for the O'Connor equation, can you go back to that slide? You have a sort of exact solution on that neighborhood or U to solve the O'Connor equation.
Yes.
Probably next slide, or I don't know.
Yes, here.
Yes, that's right. So the O'Connor, assume that for the beam solution, O'Connor actually the approximate solution globally. Here is when you mean that you O'Connor satisfy that equation exactly. What do you mean? So this U, how this neighborhood U is defined?
Yeah. So this global solution mean here's a solution on a neighborhood of the geodesic. So when we actually construct the Gaussian beams, we can use some functions to this neighborhood.
Yeah.
But initially this U is just a neighborhood of a point on the geodesic. So in a sense, we want to cover the geodesic by this set U.
Yeah.
And when we do that, we get a neighborhood of the geodesic, and I call the solution to the diagonal equation global solution of this neighborhood. But in the end, we need to have some kind of functions. And actually that also needs to be done a little bit like carefully, because we want to have something analytic in the end. You cannot just cut, if you want something analytic and you use cutoff functions, it doesn't work. You have to be careful.
Yeah, okay, I see. So then there's at the conclusion, you say that you don't need to apply like invertibility of your integral transform. So then by using Gaussian beam, have you been able to prove some results that previous, like using previous approach cannot do? So why you, in other words, why you are using Gaussian beam here to construct such kind of solution, prove such kind of results? Is that really what's a crucial motivation here?
Yeah, okay, that's actually a very good question. Thanks. So let's go to the very end.
Yes.
To this FBI transformation. So let's see it here. So yeah, very good. Thanks very much. So if you use the standard construction of Gaussian beams, which is by usually by Taylor series argument, and this is the argument where you see the Riccati equation, and of course and also in that case you will have the transport equation split into parts which correspond to the powers of tau, as I guess you asked at some point.
Yes.
Okay. So if you do it like that way, you will actually have that. You will have that this here. Sorry, let's not go there. I will check here. Okay, let's see this equation. So in that case, you will have that this O has inside tau to power minus capital K, where capital K can be anything. So it's in a sense, it's a polynomial decay to arbitrary high order, but it's not exponentially. It's not exponential decay in tau. The reason what it affects the thing is that when we go to the FBI transformation here, so now you will have here tau to power, psi to power minus capital K. And by that, and then you can study the standard wavefront set of the unknown F. So you can actually show that under the assumptions of our theorem, the unknown F is smooth on the transversal manifold, but it's not enough for the recovery. So with this exponentially accurate solutions, we get the exponential decay here, which then translates that the unknown F on the transversal manifold is analytic, and then we can recover it by boundary determination on the boundary. Without the analyticity, which translates to the polynomial decay, we can only study the smoothness.
Okay.
We actually did this on our earlier paper.
Okay. Very good. Yeah, thanks.
Yeah, thanks very much. Very good questions.
Thank you very much. Are there any other questions or comments, please?
I'm still a little puzzled about how you go from M to M naught cross R. I mean, Q and Q1 are defined presumably on M. Do you just take them to be 0 outside M, or what? Because the Dirichlet Neumann map is on M, right?
Yeah, so let's go to the very beginning. I need to go very, very early. Okay. So Q1 and Q2, they are defined on this pink set here.
Yeah.
Okay. So technically, we actually, since our Q1 and Q2 are all in L infinity, we can technically speaking extend them to the cylinder by 0. The extension is still in L infinity.
Yeah.
Right. And then when we go on, now I need to go to the place of the geometric optics solutions that perhaps tells what happens in the x1 direction, which I think was in your question.
Yeah.
So let's go with the CGO
You're
part.
thinking of Q1 and Q2 extended to R cross M0, and you're using the Dirichlet Neumann map on its boundary, then I understand everything.
Okay, so do you understand everything?
I'm not sure. I don't think I do.
Okay, right. Maybe I'll explain this. Maybe this helps. Maybe not, it doesn't. So we will use the product of U1 and U2, where U1 and U2 are harmonic functions, and especially they are these CGOs in our case. So U1 will have this term in front. U2 will have plus SX1.
Yeah.
So when we multiply them, then happens what happens usually. Exponentially large terms will cancel out. So you have e to power minus tau plus e to power minus tau minus I lambda x1. You multiply that by e to power minus tau, so plus tau, e to power plus tau. And actually we take, okay, let me try again. So U1 is e to power minus tau plus I lambda times x1. U2 is e to power tau minus I lambda x1.
Yes.
So in this case, the exponentially large factors will cancel out, and you're not left with 1. You are left with e to power 2 times I lambda x1. So this gives the Fourier transformation in the x1 direction. So this is how we deal with the x1 direction.
Okay.
Yeah, hope that helps. Thanks very much.
Well, thank you.
Thank you. Are there any other questions or comments, please?
So I have a minor remark, and you probably already know this. So in the slide where you show your two rays meeting, and then I think it's slide 6 or something.
Rays meeting.
You have a picture where the two rays are coming, and then the support, you show a small support there.
Okay, where was it? I think it was late.
Not this.
Yeah.
This one.
Yeah.
So, the condition that the sums of the two velocities add up to the c there.
Yes.
The direction, right?
Yeah.
So that that's the equal angle law of reflection.
Can you say it again, please?
So the two these are unit vector. The velocities of those rays are unit length.
Yes.
And the sum is the c. So that actually, if you figure out the geometry, it says c is the bisector of the two angles.
Bisector?
Yes.
What does it mean?
Which means, that, if you have two rays,
yeah,
and then you draw the line in the plane containing them, that's a bisector. And this is a condition which shows up actually in the hyperbolic case a lot.
Right.
Which means that if you have an interface, so which is where the jump in the Q is, and then if you send in a ray which hits it, then the outgoing ray is that, and it's exactly that condition.
Yeah.
And so now, and the other side to this is that, so you're constructing these solutions using the Gaussian beams. So of course, these are also solutions of the associated hyperbolic problem,
Yeah.
where the t along the ray is the time in that.
Yeah.
So in some sense, so once you're using these Gaussian beam solutions, then I'm just saying this very vague, I'm not even sure. You're reducing the problem to, in some sense, a two variable problem. There is the direction S, and then there is a direction T, and it's like Laplacian in two, something like that. I'm just thinking, I just.
Yeah. Yeah.
Because these Gaussian beam solutions are the solution of the hyperbolic problem with the time.
Yeah.
So and then you're combining this some of the other, so I don't know, it's sort of reducing it to 2D. I'm not sure quite how, but just that's my thing.
Yeah.
The second thing is that for hyperbolic problems, when it's trying to do unique continuation, especially the kind of Tataru, one of the ways of going about doing that, Tataru and Robiano, one of the ways of going about doing that is by taking the FBI transform of the hyperbolic operator and trying, I don't know these things very well, but trying some elliptic techniques for it. So I'm wondering, is there a way to sort of go from elliptic to sort of hyperbolic by taking an FBI transform or something? Ultimately, you're sort of using elliptic hyperbolic techniques here.
Maybe I can say to the direction to go into the hyperbolic from this elliptic setting. So that can be done, and perhaps I can say that we're actually working on that. So this method works in the hyperbolic setting.
Sorry, could you say that again? I didn't catch all of that.
I think this method, it works in the hyperbolic setting where you actually have more naturally these Gaussian beams.
Right.
So maybe I'll make a comment about, so typically, in typical geometry, you don't have, well, it is not known if you have like an analog of CGO solutions in the elliptic setting. In the cylindrical setting, you do, as I have now explained. And in that case, you do sort of like a separation of variable argument to x1, this Euclidean direction, and x prime to the transversal direction. And now you have in the x1 direction, you have sort of like negative energy, which corresponds to exponentially growing solutions. On the transversal side, then you have the positive energy solutions, which means that they're like a high energy eigenfunctions. And these you can take to be the Gaussian beams, right? So this is like it's like a feature of the geometry that you can do this kind of splitting. In the hyperbolic setting, you don't need to do this.
No.
There is always like Gaussian beams available. So that's very nice. Yeah. Also in that setting, if you want to have like exponential decay in the correction terms, you need to have by our methods, you need to have like analyticity of the known geometry.
Right.
So maybe that answers a little bit.
Yeah. So now in the earlier paper, when the geometric optics solutions were constructed, so I think that was, so when I forgot that you were involved in that too, right? In the earlier papers on such metrics with M0 cross R?
Yeah.
And there did you use, so you did not do these exponential, like you did not, when you were constructing the Gaussian beam, you didn't do the exponential things there, right? It was the same procedure, but you stopped earlier with polynomial things. Is that correct?
Yeah. And that is super well known how to do that. That you get the polynomial decay, and it sort of goes like that when you construct the solutions by Taylor series arguments, this is now roughly speaking. So if you do the Taylor series to power capital N, then your decay will be n over 2 in tau. So if you take n, the length of the amplitude very large, capital N, then your decay will be tau to power minus capital N divided by 2.
Right. So now in your solution, so I noticed that for the what is it called, the transferred equations, you did not solve to infinity, you just only went till up to n, right? Capital N?
Yeah.
But it's only your phase that you did an exponential approximation. Like, Correct. It's only the phase that you really wanted accurate to exponential decay.
Let's go to the slide.
Whereas your the coefficients, the a sub n's, right? You stopped at capital N, correct? And
Yes.
and then so probably the remainder also is okay. But your phase you chose to be much more accurate.
Phase is an exact solution.
Right. Okay. So that is where the difference is, right? Normally people stop at a polynomial approximation of the phase.
Yeah, and also for the amplitude. Here we actually solve the amplitude also exactly. So in a sense, there are like three types of approximate things in the usual construction. First, you solve the phase function by Taylor series argument to some order, quite high order. Then you solve the amplitude functions also. It's convenient to solve them to same order as the phase function. And then you, of course, have also this decaying series in tau. And then you have to decide what is the capital N.
Right.
Yeah.
I see. So you did exact solutions for the phase, and then for the amplitude exact solutions, but you went only as far as capital N terms or something.
Yeah.
I see.
And, yeah, the point is that so tau is the large parameter, and the point is that we fix tau, then we find capital N, so that we have this kind of dependence. So this is, in my opinion, this is not, at least I haven't seen this kind of
No.
N depending on tau done before. I'm sure it has been done in some papers, but I haven't seen it.
Okay.
So typically N is independent of tau.
Right.
Yeah.
Okay.
Why this works is by this Cauchy estimates and this. So why this works is we have the Cauchy estimates and this another condition for the classical analytic symbol, which was this growth decay in the index of the amplitude component A, J here. Okay. For this, yeah, just I would like to. So we used results from the paper by Sjöstrand. So it's this last one here. Of course, it's in French, so it's a little bit trouble.
So in some sense, actually, so I'm just saying that, let's say, suppose you were just doing for the plain Laplacian plus Q. So this gives another proof of just the, the basic Sylvester-Ullmann result from the beginning, but without using Fourier transforms, but more about analyticity, I guess.
Yeah, I think you're almost correct, but we actually consider the linearized Calderón problem. So that's the problem which is super easy to solve.
I see. I see. You linearized about. Okay.
Yeah, but you're definitely thinking it the correct way. Yes.
I see. Okay. Interesting.
Thank you very much. Are there any other questions or comments, please?
Quite late. Yeah.
Okay, if not, thank you very much, Tony, for the very nice talk. Thank you very much, everyone, for coming. Thank you very much.
Thank you all.